and it's a real honor for me to be here. So today we are going to talk about the future of the universe. But we should remember that the universe is big. Okay? In fact, the part of the universe that we can see today is about 45 billion light years in diameter, in radius. Okay? So the future that I'm going to talk about, okay, will also be over a very, very long time scale, spanning tens of billions of years. Okay? So it will probably not have anything to do with our near future. Okay? So let me begin the story about 100 years ago. Okay? At least this is the time when the story started getting understood. Okay? And about 100 years ago, many people, okay, realized that our universe is expanding. Okay? And it's expanding in a very systematic fashion. Okay? Namely, that faraway objects are moving away from us, and further away they are, the more is their speed. So this has come to be known as the Big Bang theory, and by now, in fact, there are plenty of experiments that confirm. So by the middle of 1990s, we had a good understanding of this Big Bang theory. And what people had thought at that time was that the universe consists mainly of two kinds of sources of energy or mass density. Okay. It has ordinary matter like stars, interstellar dust, etc. Okay. And it has something called dark matter, okay, which is some strange kind of object. We still don't know what dark matter is. Okay. But as far as their gravitational properties are concerned, they behave exactly in the same way as ordinary matter. Okay. So the dark matter attracts like ordinary matter. And it was also believed that because gravity is attractive, okay, the pool of matter was slowing down the rate of expansion of the universe. Okay. So it's as if you have thrown a ball up. Okay. So the ball is going up because there is some initial condition which set it in motion. But as the ball goes up, because of the attraction of the earth, its speed will slow down. Okay. And it was believed that the universe also behaves this way. Okay. Some explosion in the past started this expansion. But because the universe is full of matter, the attraction of the matter will slow down the expansion. So this changed in 1998, okay, when there are two independent experiments, okay, which made a profound discovery. Okay, so these are the names of these two experiments. Okay. And what they found is that the expansion is actually accelerating instead of slowing down. So instead of the rate of expansion becoming smaller and smaller with time, okay, it's actually becoming larger. So this, of course, completely changed our view of what the universe consists of. Okay. And at present, the best understanding that we have today, okay, is that 73% of the energy density in our universe exists in some unusual form, which is known as dark energy, or which is also called the cosmological constant, because that's what Einstein had introduced long time ago. Okay, so Einstein in fact introduced this concept of cosmological constant, but then he said that the universe actually doesn't have that constant. Okay, but now we know that it does have. So this dark energy, okay, is unusual because it has negative pressure, and it's this negative pressure that causes gravity to act as a repulsive force. Okay. And that's the reason why the universe accelerates instead of decelerating. So the remaining 27% is thought mostly of made of ordinary matter and dark matter. Okay. So this is the base model of the universe that we have today. Now this discovery, okay, although it sounds technical, okay, this in fact has drastically changed our perspective on the far future of the universe. And that is what today's talk will be on. Okay, what does it say about the future of our universe? And it is also going to be the story of our future, okay, provided of course we survive pandemics, nuclear war, climate change, asteroid impact, and whatever other exciting things may happen in the future. So I'll begin with what I'll call the classical story. Okay. This is classical because this is a story without quantum mechanics. Okay, so first we will ignore the effect of quantum mechanics and see what the dark energy tells us about the future of our universe. So now we have already seen that presence of dark energy causes the universe to undergo an accelerated expansion. Okay. And this in fact is a consequence of Einstein's theory of gravity. Okay. Once you have this matter with negative pressure, okay, then Einstein's equations tell us that this is the way the universe will evolve. Okay, you don't have to make any further assumption about the theory. Another strange consequence of dark energy is that dark energy density remains constant as the universe expands. And this is very unlike ordinary matter, which gets diluted, because the usual experience says that if you have a certain amount of matter, and if the universe is expanding, then the same amount of matter is spreading over a larger volume, so its energy density will go down, its density will go down. This, however, does not happen for the dark energy. Because of the negative pressure, okay, what happens is that as the universe expands, that negative pressure creates more dark energy. Okay, and what one can show, again as a consequence of Einstein's equation, is that the energy density in the dark energy remains constant as the universe expands. And this means that the acceleration will in fact continue in the future. It's not going to stop. Okay. And one can estimate how fast the universe will expand in the future, and what one can show is that the size of the universe will double in about every 12 billion years. Now, due to this accelerated expansion, it turns out to be physically impossible for us to reach very far away places in the universe. In fact, one can show, okay, again from the theory of gravity that Einstein wrote down 100 years ago, that even if we travel at the speed of light, okay, we can at most reach objects which are at a distance of 18 billion light years from us today. So the objects that are further than that are moving away so fast that even light cannot reach them. And this seems very strange, because today, for example, we can see parts of the universe that are about 45 billion light years away from us. Okay. But much of that part we can never reach, even theoretically, okay, however fast we travel. Technically, we say that these objects are outside our horizon. Furthermore, okay, as the universe expands, more and more objects will go out of our horizon. Okay, because if 18 billion light years is the limit, okay, then objects which are closer than 18 million light years from us today, okay, they'll eventually become larger than 18 million light years and they'll go out of our horizon. We'll never be able to reach them. Okay. So it's as if the universe becomes a multiverse, okay, and multiverse in this case corresponds to multiple universes which cannot communicate. Okay, even in principle, you cannot travel from one part of the universe to another part of the universe. Now, there is an exception to this. Okay. While on the average, every object in the universe is pulled away from every other object, okay, we also have local gravitational force which binds parts of the universe together. Okay. For example, if we think of the solar system, okay, the solar system is not going to be torn apart by the expansion of the universe. Okay. Neither will our galaxy be torn apart by the expansion of the universe, because the various stars inside the galaxy have their mutual gravitational attraction, okay, which will hold them together. Okay. But different galaxies can be pulled apart by the expansion of the universe. Now, our nearest large galaxy is Andromeda, okay, but Andromeda is in fact coming towards us. Okay. And one can estimate based on its motion today that it's going to merge with the Milky Way in about 10 billion years from now. Okay, so even Andromeda is not going to be pulled away from us in the future. But most other galaxies that we can see today will eventually go out of our horizon. So if we want, we can in principle establish civilizations in those galaxies today. Okay, if we send out spaceships at a sufficiently high speed, okay, we can reach those galaxies and we can establish civilizations. Okay. But eventually they will go out of our horizon and we will lose touch with those civilizations forever. So in the far future, our local group of galaxies will be the only ones that will be within our horizon. And when the last star in that group dies, okay, life as we know today will not be possible. Okay, because today at least we know the life forms are supported by the energy from the stars. And this is expected to happen over a period of 10 to the 13 to 10 to the 14 years. And that will be a somewhat sad and lonely end to our civilization. Okay, we will die our natural death, but we will have no communication with our cousins who may be living in other galaxies. So this is our understanding of the future of the universe as far as the classical physics is concerned. We will see that in the quantum world, life will be a bit sadder, but it will be more exciting and adventurous. And this is the story I am going to turn to, the quantum world. So the quantum story. So this story begins with by considering a simple system. Let's imagine that you have a hill with two valleys and you have a particle that slides along the hill. Now our everyday experience tells us that the particle can be at rest either at A or at B. Okay, everywhere else it cannot be at rest. Okay, it will slide down. Let's suppose that the particle is at rest at A. Okay, higher of the two valleys. Now everyday experience based on our classical physics tells us that it will continue to rest at A forever unless it's disturbed. Okay, that's our classical understanding of what happens when a particle rolls on a hill. But according to quantum mechanics, there is a tiny probability that a particle which was sitting at A may suddenly disappear and appear on the other side of the hill, and from there it can slide down to B. So this phenomenon is called quantum tunneling, but there is no physical tunnel. Okay, you don't dig a tunnel to go from A to B. Okay. If you are sitting at A, okay, quantum effects can suddenly make it appear on the other side of the hill, and from there it slides down to B. This probability typically is very, very small. Okay, so you don't worry about it and you don't see it in everyday life. Now our interest of course will not be in a particle, but in the whole universe. But it turns out that the dynamics of the universe can be understood, okay, to a great extent by just considering the example of a particle. So dynamics of the universe is described by what we will call a quantum field theory, okay, or a more general version of this is what we call string theory. That's the subject I work on. But for us, we should just keep in mind that a field, okay, what we mean by field is like having a particle, okay, but imagine that there is a particle sitting at every point in space, okay, and then that particle can move in some hidden directions. Okay, those hidden directions are not physical directions, okay, but just imagine that you have a particle at every point in space and the particle is able to move in some hidden directions. And we will consider the simplest kind of field, which is called a scalar field. Okay. a scalar field has only one hidden direction. Okay, so it's as if you have a particle at every point in space, and that particle, each of those particles can move in one hidden direction. And just like the motion of a particle on a hill is controlled by the gravitational potential that the particle experiences, the motion of a scalar field is also controlled by some potential V. Okay, and that's what plays the role of the height of the hill. So let's suppose that you have a scalar field with a potential with two minimum, just like a particle on a hill. Okay, two minimum A and B. So if you have a scalar field, okay, with a potential of this form, then the scalar field can be at rest at other minimum. Okay. So scalar field, again let me emphasize that you think of this as a particle sitting at every point in space. Okay. So it can be in two stationary positions, one where particle at every point in space is at the position A in the hidden direction. Okay. The other stationary configuration is where the particle at every point in space is in the position B in the hidden direction. Okay, these are the two configurations that you can imagine. Okay. And these two configurations can be thought of as two phases of a scalar field theory. Okay. The phase, the word phase I am using here, okay, is in the same sense as we talk about phases of matter. Okay. We know, for example, that ice and water are two phases of H2O. Okay, they are very different realizations, okay, but they are just two phases of the same theory. In the same spirit, we think of these two different configurations, a scalar field, which is particle at every point sitting at the position A in the hidden direction, and a particle at every point sitting in the position B in the hidden direction, as two phases of the universe. Okay, the universe can either be in phase A or in phase B. Now typically the properties of these two phases are very different. Okay. If you are in phase A, okay, we will see some elementary particles like electrons or other elementary particles, photon for example, the carrier of light. Okay. In phase B you may see a completely different kinds of elementary particles. Okay. In general, the kind of elementary particles that you see, what kind of interactions they have are quite different in these two phases. Okay, that's why we call these two phases of matter. Okay, these are like, as we know, the properties of ice and water are very different, even though they are two phases of the same underlying theory. Okay, in the same, by following the same analogy, one can show that the phases of A and B have very different properties. Okay. And in this context, I can also tell you what dark energy corresponds to. Okay, dark energy has a natural explanation in the context of the scalar field theory. Okay. It is simply the value of V at the local minimum. Okay. So for example, in phase B we have positive dark energy, okay, and in phase B we have negative dark energy. Okay. And we know that in our universe we have positive dark energy. Okay, so if our universe had two phases, we are in phase A. Okay, now let's consider the effect of quantum mechanics. Okay. So for this again, let's go back to the case of particle on a hill. We have seen that if you have a particle rolling on a hill like this, okay, then particle can be sitting either at A or at B. If it sits at A, then classical laws tell us that it will sit there forever. Okay. But quantum mechanics tells us that there is small probability of its tunneling to B. And we now want to ask if a similar event can happen in a quantum field theory. So this is the question you want to ask. Can a similar tunneling happen in a quantum field theory? Imagine that you have a scalar field with a potential like this. Okay. It can be either at A or at B. Okay. Suppose it's at A, which means the universe is in phase A, everywhere the particle is sitting in the position A. Okay. Can it happen that it makes a transition suddenly into phase B? Now what one can show is that it does not happen everywhere simultaneously. Okay. Imagine that we have a particle at every point in space sitting in this position A in the hidden direction. Okay. The probability that everywhere in the universe suddenly it will jump from A to B, okay, is actually 0. One can calculate this and one can find that that cannot happen. Okay. But there is something else which can happen, okay, which is that some small region of the universe, okay, in some small region of the universe, particle can go from phase A to phase B. Okay. So this is a picture in physical space. Okay. What may happen is that you have a universe where which is in phase A, which means the particle is sitting at the position A in the hidden direction everywhere. Okay. And then in some region of the universe, it can suddenly jump from A to B. So this is what we call a bubble. Okay. We produce a bubble of B inside phase A. Okay. Then the question is what will happen to the bubble afterwards. Okay. Now once quantum mechanics has produced such a bubble, okay, then you have to apply classical laws to see how the bubble is going to evolve. Okay. And here, as we know in classical mechanics, okay, everything wants to lower its potential energy, right? If I drop a particle, okay, it drops on the ground because it tries to lower its gravitational potential energy. Okay. And this is no exception. It will try to lower its potential energy. Now, there are two competing effects here. Okay. So first of all, the potential energy density is lower in phase B than in A, right? That's what you see from this picture. B has a lower potential energy density than in phase A. So if the bubble expands, it can actually lower its potential energy. Okay. But at the same time, okay, because you are making this change from B to A, there is some kind of surface tension that is the energy proportional to the area of the bubble, of the surface area of the bubble. Okay. So if the bubble expands, then the surface energy increases, right? So there is a tug of war between these two effects. Okay. So the surface tension tries to pull back the bubble to 0 size, and the potential energy tries to expand the size of the bubble. Okay. What one can show is that there is a critical radius of the bubble. If quantum mechanics produces a bubble of a sufficiently big size, okay, then it becomes energetically favorable for the bubble to expand. You can lower the potential energy by expansion of the bubble. So this is what I have said. If a sufficiently large bubble of B is produced, then surface tension can be overcome. And once that happens, the bubble begins expanding and in the process lowers its potential energy. Okay. But of course, the total energy is conserved, so that potential energy essentially goes into the kinetic energy of the surface. Okay. So the bubble wall starts expanding faster and faster. Okay. And this you should not confuse with the expansion of the universe, right, which happens everywhere. Okay. Here, the bubble is produced by a quantum effect, and once this bubble is produced, then it starts expanding within the phase A. So the surface begins an accelerated expansion. Okay. In that process, it converts the potential difference to kinetic energy. Okay. And soon the speed of expansion of the surface approaches the speed of light. Okay, because it's constantly accelerating by absorbing the potential energy. Okay. And eventually, it's going to convert A to B everywhere within the horizon. Okay, even the bubble cannot go out of the horizon, right? I said the horizon is the limit of how far light can travel, right? And the bubble wall also expands at the speed of light. So horizon, it cannot go beyond the horizon, but it can go all the way up to the horizon. So anything within the accessible universe, it converts from A to B. Now, given this, now we can ask what will be the fate of any object in A during this process. Okay, imagine that we have some planet in the phase A, okay, some life in phase A, right? What will happen to them when this bubble of B reaches them? Okay. And the answer is in fact simple. There will be total instantaneous destruction of anything that exists in A. Because even the elementary constituents like the electrons, right, which are the fundamental building blocks of the matter in A, they do not exist in B. As I said, the kind of elementary particles that you have in A are very different from the kind of elementary particles that you will have in B. Okay. So once this bubble of phase B reaches any object in A, it just wipes it out completely. Okay, it may produce new objects in B, but not the kind of object that were present in A. Okay. So from the point of view of objects which are in phase A, right? Imagine that you had a planet where there's life in phase A. This bubble of B will be called the killer bubble, because once it reaches you, you are gone. And A is known as the false vacuum. It's called the false vacuum because it gives the impression of being the vacuum where nothing ever happens, right? The field sits at the bottom of the potential, nothing moves, except that once in a while a bubble of B is produced and the killer bubble just comes and wipes it off. Okay, so it's almost a vacuum, but not quite, because once in a while it can get wiped off. So with this, now we turn to the central question that concerns us, okay, and that is, are we living in a false vacuum? Okay, can this happen to us? That suddenly a phase which corresponds to a lower potential energy than what we have today just comes and wipes us off. So the possibility that you have been living in a false vacuum has in fact been known for about 50 years. But there are some recent developments which have generated renewed interest in this subject, because in 2012 there are experiments at CERN which discovered the first example of a scalar field in nature. Okay, earlier, of course, people had theoretically predicted the existence of scalar fields, okay, which is called the Higgs particle. Okay. But the first example experimentally was discovered in 2012. Okay. So that's what is called the Higgs field. So given this existence of a scalar field, now we can ask, are we living in the false vacuum of the Higgs field? Okay. The theory of the Higgs field is reasonably well understood, so we can ask this question: are you at the minimum of the potential, absolute minimum, or only a local minimum? Now when we write the theory of the Higgs field, okay, we write a nice form of V, right? Because nobody wants to start with a theory where our universe is in a false vacuum. Okay, so when the theory of the Higgs field was written, okay, people took a potential which has a minimum like this, okay, and it was understood that we are living at the minimum of the potential. But it turns out that the quantum mechanics spoils the game again. Okay. So there are different kinds of quantum effects, not the kind of effect that I talked about, the tunneling. Okay. There are different kinds of quantum effects which actually corrects this potential. Okay. And as a result of that quantum effect, okay, there is another minimum which is developed of the Higgs field. Okay. We are at this one. Okay. We are at the left minimum. Okay. The right one is something that we didn't ask for, but quantum effects actually produces it. Okay. So we can ask, are we at the true minimum of the corrected V? Right? Are we on the left? Okay. We are on the left, that we know. Okay. But is the right one lower than us or higher than us? Right? Because that will determine whether we are living in a false vacuum or a true vacuum. Unfortunately, we don't know the answer yet. Okay. Because to know the answer, you have to know the parameters of the Higgs potential very well. Okay. And current experiments, although they have done quite well to fix the parameters, okay, they are not accurate enough to tell us whether the new minimum that we find, okay, is actually below us or above us. It seems that it's most likely below us. Okay, if you look at the mean, okay, there is a distribution, of course, of the parameter space. Okay, but the mean of the distribution is actually where the potential is below us. Okay, so most likely we are in a false vacuum of the Higgs field. Fortunately, we don't really have to worry about this very much, okay, because one can show that even if you are living in a false vacuum of the Higgs field, okay, the probability that a killer bubble of the Higgs field will be produced anywhere is extremely small. Okay, that you can estimate, because just from the fact that the parameters are known to in a certain range, right, we can take the worst possible case and we can ask, given the worst possible case, what is the probability that such a killer bubble will be produced? Okay. And that turns to be extremely tiny. Okay. So it's extremely unlikely that it will ever be produced before the natural death of the galaxies. Okay, so you don't really have to worry about the false vacuum of the Higgs field at present. But the full story, in fact, is more complicated. It's more complicated because there are theoretical reasons to believe that there may be many more scalar fields in our theory. Okay, we just haven't discovered them because we have not probed high enough energies. And among these unknown fields, there may be some whose false vacuum describes us. Okay, it's like instead of having just one hidden direction, right, which is represented by the Higgs field, there may be many hidden directions in which the particle can move. Okay, and we have only explored one direction, okay, where the potential, even if it's lower than what we are today, okay, it's not very much lower, okay, so that the transition probability is small. Okay, but there may be other directions, okay, in which there is a high probability of producing false vacuum, right? We don't know. So the probability of producing killer bubble for these fields may be large enough to cause us worries. So we can again go back to the question, are we living in a false vacuum? How do you know the answer to this question? And we could answer this question if we had a fundamental theory. Right? And what we mean by fundamental theory is a theory where the list of fields and the potential is fixed from some fundamental principles. Okay? Then we could do a first principle calculation and see if where the particular minimum that describes the phase of the universe that we are in, okay, whether that is the lowest minimum or whether there are other minimum which are lower than us. Now string theory, that's the subject that I work on, okay, is an attempt to have such a fundamental theory. Okay. It's a proposal for a theory that describes all the elementary particles and their forces, including gravity. And according to what we understand about string theory at present, okay, it has many scalar fields with complicated potential, with many local maxima and minima. Okay, here I have only drawn a figure in one direction, okay, but actual picture in string theory is that you can think of this as a multi-dimensional space, okay, of many scalar fields. There are many ups and downs, okay, in all directions. We know a very small fraction of those, okay, most of those are still to be explored. Okay, that's the current picture of what of the kind of phases that string theory can give us. So if string theory is the right theory of the world, okay, then one of these minimum will describe the phase of the theory you are living in. Unfortunately, we do not yet know of a phase that describes exactly the elementary particles we see. Okay. Because if we could identify a particular phase of string theory that describes our phase, okay, then in principle we can calculate everything from there. Right? We can predict the masses, the charges of elementary particles, what kind of interactions they have, whether we are at the absolute minimum or only a local minimum. Right? All these questions could be answered if we could identify which particular of this minimum describes the universe that we are living in. That we do not know at present. So even if string theory is right, the statement that we can make today is that we do not know our position in the landscape. Okay, this is what is called the string landscape. Okay, many ups and downs. And you have to imagine this not as a one-dimensional picture, but a multi-dimensional picture. But nevertheless, we are not totally in the dark. Okay, we can say something based on our understanding of string theory. Okay. And that is the following. Okay, it's a combination of an experimental input and a theoretical input. Okay. We know that the dark energy density that we see today is positive. Okay. And I had told you earlier that dark energy density is the value of the potential at the minimum. Okay. So the fact that the dark energy is positive tells us that the phase that we are living in, the potential is positive. On the other hand, from theoretical studies, we know that string theory has many phases with zero or negative potential. Okay, none of these describe us. Okay, but it certainly has many phases with zero or negative potential. So which means that we are not at the absolute minimum, right? Because for us the potential energy density is positive, and we know that string theory has other minimum where the potential energy density is either zero or negative. So you are not in the absolute minimum, and that means that we must be living in a false vacuum. Okay, there are other vacuum which have energy density, potential energy density that is lower than us. So given that you are living in a false vacuum, we can ask how likely is it that we shall be hit by a killer bubble during the next 1 year. Okay, this is a question we could ask. If we knew our position in the landscape, we could answer this question. Okay, we could give you the precise probability of being hit by a killer bubble in the next 1 year. But this unfortunately is not known, right? We don't know our position in the landscape, so you cannot calculate what the probability is. But we can rely on the experimental data. The data that says that we have lived for so long. So the current age of the universe is about 14 billion years. Which means that the probability that the risk of a hit per year shouldn't be very much larger than 1 in 10 to the 10. Because if it was larger than 1 in 10 to the 10, then most likely would have been wiped off today. Now of course, in quantum theory, when you talk about probabilities, right, you always have to think in terms of most likely. Right? It could even happen that the actual hit probability is much lower, much higher, but we have just been lucky to survive. Okay, but assuming that we have not been extremely lucky, and this is the we are in a generic situation, we can say that the risk of hit per year should be less than 1 in 10 to the 10, because otherwise you would have been wiped off anyway by now. Now 1 in 10 to the 10 is a small number, okay, but I mean, you are not very used to very small numbers or very large numbers, right? So you can ask, can we visualize it? Okay, what is 1 in 10 to the 10? Okay. And here is an estimate of what is 1 in 10 to the 10. So let's imagine that one day a small asteroid hits the Earth and destroys everything within 100-meter radius of impact. The chance that you will be within that region is about 1 in 10 to the 10. Okay, so that's how small a number it is. Okay. So this is the bound that we can give on the probability that our universe will not be wiped out in next 1 year. Okay, of course, the actual probability may be much lower, right? We can only give an upper bound. Okay, but this is the best we can say. Now it turns out that the actual story is a little bit more scary. It's a little bit more scary because as time progresses, one can do a simple calculation to show that our risk of being hit by a killer bubble in a year is increasing. Okay. And the way to understand this is that our universe has a certain age, okay, and as time progresses, okay, the bubbles that are farther away, which are produced farther away, can come towards us. Okay, because it has more time to travel. Okay. This is the physics why the risk of a hit per year is increasing. Okay. And one can do a somehow detailed calculation to show that the risk today is about 3.7 times larger than the past average risk. Okay. This past average risk is this 1 in 10 to the 10 that we mentioned. Okay. And the risk in the far future will be about 15 times larger than the current value. So not only that life in the universe is risky, it's in fact getting more risky with time. So I promised you that quantum theory will have excitement, and I hope you would agree that the possibility, however small, that tomorrow you may be wiped out by a killer bubble, and the rest of the universe will share the same fate, is more exciting than waiting for a slow death over billions of years. Now, I promise you two things, right? That quantum theory will be more exciting and more adventurous. Now, it's more exciting, but it's not yet more adventurous, right? Adventure requires you doing something. Okay. So that will be the last part of my talk. Okay. What kind of adventure can we have with the killer bubbles? And it turns out that as in most adventures, okay, we need to leave home. Okay. So let's recall some of the facts that we have learned. First, we learned that at present we can access a certain region of the universe that is given by our horizon size. We also learned that with time, the expansion of the universe will convert this into a multiverse with many universes. Okay, because what is within our horizon today will not remain within our horizon tomorrow. And the rate of increase of the number of distinct universes is controlled by the expansion rate of the universe. Okay, this is just Einstein's theory of general relativity. The other thing we learned is that the killer bubble, so the rate of expansion rate is known very well. Okay. So the rate of increase in the number of distinct universes we can calculate and we know very well, right? The universe doubles in size once in 18 billion years. Now we learned that killer bubbles will make some of these universes unlivable, okay, but the rate of destruction is not known at present. Now if it turns out that the rate of universe production exceeds the rate of universe destruction, then the number of livable universes will increase with time. Right? Because we saw that even killer bubbles, right, if it's produced within one universe, it can at most go up to the horizon. It cannot destroy the universes that are lying outside the horizon. Okay. So it can only destroy a single universe, not the whole multiverse. Okay. A single killer bubble can only destroy a single universe. So this of course is a wishful thinking that the rate of universe production exceeds the rate of destruction, but if it does happen, okay, then the number of livable universes will increase with time. Okay. The question is, how does it help us? Okay. And it turns out that it doesn't help us if you are lazy. So if we remain confined within our galaxy, then our annihilation probability will be controlled by the rate of destruction. Okay. The fact that more and more universes are being produced by this expansion of the universe is of no relevance. Okay. Once a killer bubble is produced in our within our horizon, will be wiped out. Now, of course, this rate may be small enough so that the killer bubble reaches us after the galaxy has burnt its fuel, and we have perished anyway. Right? We saw that our galaxy will probably survive for about 10 to the 13 to 10 to the 14 years. Right? So if a killer bubble is produced after 10 to the 20 years, we don't care. But it will be a pity if we perish when the galaxy still has a lot more time to go. Right? We don't want to die after 10 to the 10 years, right, if the galaxy is surviving for 10 to the 13 to 10 to the 14 years. Now it turns out that if we can overcome this fate if we spread out into the currently accessible universe. Right? Today our horizon size, right, we have a certain size horizon, we said 18 million light years, right, and in principle if we try hard enough, right, maybe we will not reach 18 billion light years, but we may reach 10 million light years. Okay? That's still some progress. Okay. Once we spread out, okay, then over time this region will split into many universes. Okay? That job will be done by the dark energy, because dark energy makes this universe expand, and even if you are able to spread out within say 10 million light years, okay, the dark energy will eventually separate them out into distances beyond 18 billion light years and will be forming different parts of the multiverse. And in that case, even if some of them are destroyed by the killer bubble, the others will survive. And this way we can extend the collective life expectancy of our civilization. Right? No single civilization can increase its life expectancy, but if we take the collection of all the civilizations that we may establish this way, okay, then the collective life expectancy, by which I mean the expected lifetime of the last civilization, okay, can be increased. And in fact, one can do a quick calculation and show that if we manage to spread into n universes, then the life expectancy will be increased by a factor like this. Okay, so even 2 universes will increase the life expectancy by 50%. Now, in case you feel that, okay, we will be the heroes of this adventure, let me remind you that the dark energy is the real hero of the story. Right? All we can do is to somehow spread out over the currently accessible universe, and then it's the dark energy which is going to push us apart, okay, and make us go into different multiverse, be different parts of the universe, right? Different universes. Without dark energy, there is no horizon or multiverse, and a single killer bubble will basically destroy the entire universe. So this brings me to the conclusion of the talk. So I have said many things, but probably most of you will forget most of it soon. Okay. So I have tried to summarize my conclusion in just one sentence, okay, which you may remember a little longer. Okay. And that's this. Okay. Dark energy helps those who help themselves. Okay. So in your spare time, think of ways to populate the universe within our horizon. Thank you.
Thank you. Are there any?
A very fascinating story about that killer bubble. So while I was hearing, because I am not an expert in this area, it is very similar to this nucleation and growth kind of thing.
Yeah, it's in a phase transition, for example, right? Suppose you have a super cooled water.
Yeah.
Okay, and some ice pocket
Some
forms,
small
and
ice
then
crystal
exactly,
forms.
and then it starts growing,
Growth.
right?
Yeah, so
Exactly,
very
it's
similar to
exactly, the physics is exactly the same.
Yeah. Okay. Another questions. While you were saying that this hopping from one side to another side, from positive energy to the negative energy, in that case, are you assuming that this small killer bubble will form from a very small substance? Because from a very fundamental quantum knowledge, we know that quantum mechanics only works for a very tiny mass.
Yes, so the size of the killer bubbles will be microscopic.
Microscopic.
Yes.
Okay.
And the point is, you can, of course, quantum mechanics allows also big size killer bubbles, but that probability will become smaller and smaller.
Very small.
Right?
Yeah.
So what we need is that you have to form sufficiently small, sufficiently large size to overcome the surface tension effect. Right? That's still a microscopic number.
Okay.
Right?
Thank you.
And that's what controls the transition probability. Right? If you know the parameters of the potential, then you can actually calculate what the transition probability is.
Thank you.
Very fascinating talk. I'm a biologist, but I always wondered about this universe expansion, as I don't understand much. I talked to some of the string theorists in your institute. They given explanations, but still, I'm still in the instead of the dark matter much more. But the question to you is, we thought of always there's a single universe. You're saying when the universe is expanding, which is expanding, how do you get the multiverse? I mean, in which way you get the multiverse? It's a too naive a question to you, but where are the multiverses coming from?
Yeah, so it's not that there is a hard boundary between these different universes. Indeed, but starting from our place, right? If we send out a light signal, right, which is the fastest we can proceed, we cannot access the whole of the universe. Right? That's the notion of a multiverse. Right? That they cannot communicate. So, for example, our observed universe is 45 billion light years in radius, right? But we can only reach today 18 billion light years. Right? So that means if we take the observed universe, it's already split into 15 multiverses, 15 universes which cannot communicate with each other. Right? So that's the concept of multiverse. It's not that there is a sharp boundary between these different universes. Yes, it's part of a large universe. It's just that they are not being able to communicate.
Professor Sen, may I ask you a slightly unrelated question? What was before Big Bang, before the Lemaitrier's egg? What was there before it?
We don't know, we don't even know whether the question makes sense, because at Big Bang, the notion of space, the universe becomes so strongly curved that even the notion of space and time breaks down. Okay? So it's not even clear that it's, meaning we are thinking of what is before Big Bang, because we think that we have a notion of time. Okay? But it's not clear that even the notion of time makes sense at that, when the universe becomes so strongly curved. So we don't really know how to answer this question, because we don't know what's going on at the singularity, right? Whether the question even makes sense, we don't know.
What limits there exists only one killer bubble expanding up to only one universe? This appears to be an assumption, or is there?
No, it follows from Einstein's theory of gravity, right? Einstein's theory tells us how light signal propagates, right? And the wall of the killer bubble propagates at the speed of light, right? So it propagates exactly in the same way as a light signal, right? And as you say, light signal, it follows from Einstein's theory that it can only go up to the horizon, right? That's 18 billion light years in our universe today. And so that's the limitation also for the surface of the killer bubble.
Yeah, but that one, the photon which travels up to the horizon, what limits it to disappear after the horizon?
Oh, because the ones beyond that are going away faster, right? So when you say the photon is not going to stop, right? But when I say it goes up to the horizon, it goes. So okay, let me make this more specific. That today what we see as 18 billion light years from us, okay, that is the distance that we can explore by the photon, right? So what's going to happen is that when we start the photon starts traveling. What is 18 billion light years from us today is also traveling, right, by the expansion of the universe. So it goes farther and farther away. So the photon never stops, but photon never reaches that point. Right? That's the physics of this, why the photon cannot reach it.
But in that way, a killer bubble also can annihilate as it propagates or it expands.
Yes, certainly. It propagates, but it cannot reach the points.
It loses its property of killing. That's what I want.
No.
Or its intensity of killing.
No. It propagates with exactly the same intensity. Right? It's just that the points which are farther than 18 million light years, they are going away so fast that by the time killer bubble has reached 18 million light years, right, they have gone beyond 36 billion light years, right? So this way, the killer bubble can never catch them up. Right? That's the point.
Yes, go ahead.
Professor Ashoke Sen, congratulations for an excellent talk.
Okay.
I am wondering, the way you have explained it, can we just portray this phenomena in the form of the gravitational phase function?
Gravitational physics.
Yeah, gravitational phase function. Of course, you explain it as a phase function, but can we correlate it with the gravitational phase function? Because we talk about the effect of the gravity in the expansion of the universe.
Yes, so certainly much of what I described is based on gravitational physics, right? Because the expansion of the universe, right, and for example, how far the killer bubble can travel, all this is part of gravitational physics. Right? The production of the killer bubble itself is quantum physics. Right? So gravitational physics certainly is very much part of what I described.
Because it will be entirely new concept to name it and correlate it as a gravitational phase function.
As gravitational
Phase transition.
Okay, it's not gravitational phase transition, right? What I described, there may be other kind of phase transition which is gravitational, as you say, but what I described is purely within quantum field theory, which is much better understood, right? We don't know what gravitational phase transition will correspond to, but quantum field theory phase transitions we do understand, right? So the killer bubble that I described is just a quantum field theoretic effect, and then the subsequent expansion, right, is gravitational effect.
Any other question? So I have one, Professor Sen.
Yes.
What determines the surface tension of this bubble?
Okay, so that's because what happens is when the I think my slide has gone. If you remember the potential, it has these two potentials, right? And across the surface, it's changing from A to B, right? So the field has to change from the position A to position B, okay? And that causes some intrinsic energy, right? There's a gradient energy of the field, right? If the field doesn't want to have any gradient, right? If you have to produce a gradient, then it costs energy, and that's the surface tension, right? Because it is changing from A to B across that surface.
So Thank you very much for a
Thank you.
really wonderful lecture. Please join me in thanking Professor Sen again.